Hey everyone, it's Justin again. Up to now, you've learned a lot of tricks and shortcuts you can use to factor special polynomial products. But most polynomials aren't going to be a difference of squares, or a perfect square trinomial, or even have a GCF. In this video, you're going to learn how to use the grouping method to factor any quadratic function. By the end of this lesson, you will be able to factor any factorable quadratic expression. To get to that point, first, I'll give you a quick description of why this final method, the AC method, is necessary. Then we'll write down the steps to factor using the AC method. We'll practice following the steps on some examples, and then you'll have a chance to try it yourself. Some polynomials are made by multiplying by a monomial, others by multiplying the same binomial, and others by multiplying almost identical binomials. And we have easy shortcuts for factoring any of these kinds of polynomials. But what about all the other times when we just multiply random binomials? Is there a pattern we can follow to factor those? Of course. And it's all based on this step, where we combine the middle terms into one. When we're trying to factor most quadratic functions, we need to know what two terms came together to make this middle term. The problem is, there are a lot of possibilities. And if we throw in negative numbers, there are even more possibilities. Infinite possibilities. So we need a way to narrow it down. We can use what's called the AC method. You see, we can refer to the three integers in this quadratic function as a, b, and c. B is the number we're trying to split up, and the clue is in a and c. Because of how distribution works, the product of these two numbers will have a pair of factors that also add up to b. It looks complicated, but it's actually super similar to when we learned how to factor basic quadratics, except now the leading coefficient also matters. There are a lot of steps, so let's write them all down. First, find a pair of numbers that multiply to make the product of a and c, and add together to make b. Next, split b using that combination you found. Group together the first two terms and the last two terms, factor out the GCF of each group, and then those two GCFs become one factor, and the matching leftovers are the other factor. Take this quadratic, for instance. Negative 7x could be made by adding lots of different combinations of numbers together. So to narrow it down, we multiply a and c. In this case, that's 3 and negative 6, and find all the factor combinations for negative 18. There are only 6 possible combinations, which is much better than the infinite possibilities we had before. Now we just need to find which combination adds up to negative 7, which ends up being negative 9 and 2. These numbers tell us how to split up the middle term. This next step is where the term grouping comes from. We group the first two terms together, and then the last two terms together. Each group will have a GCF. In this example, the first group has a GCF of 3x, and the second group has a GCF of 2. If you've done it right, you'll notice that what's left over in each group after you factor out the GCF will match. This is a sign that the grouping method is working. From here, the two GCFs, 3x and 2, get combined to make one factor, and the matching leftovers will become the second factor. At this point, we should be done. But let's check our answer just to make sure. Take what we believe to be the factors and distribute. We get 3x squared minus 9x plus 2x minus 6. Negative 9x and 2x are like terms, so we can combine them into negative 7x. We've ended up right back where we started, proving that the factors we found do indeed multiply to make this trinomial. Remember that when we factored this, we split b into negative 9x and 2x. That step of splitting b reversed the act of combining them into negative 7x. That's why we have to split the middle term. It's how we undo combining like terms. Let's try it out. First, we multiply a and c. That would be 2 and negative 5. And now we need two numbers that multiply to make negative 10 and add together to make 9. That combination is 10 and negative 1. Now we know exactly how to split that middle term, 10x and negative 1x. At this point, with 4 terms, we can group them into pairs. Notice how the minus 1x became plus minus 1x, so we could group the negative with the 1. The GCF of the first group is 2x, with a leftover of x plus 5. And since the second group starts with a negative coefficient, the GCF here is negative 1, with x plus 5 left over. The two leftover pieces match, proving to us that we've used the grouping method correctly. The first factor will be the GCFs combined, and the second factor will be the leftovers that matched. So the factored form of 2x squared plus 9x minus 5 is 2x minus 1 times x plus 5. Take a moment to check this answer and prove to yourself that it's correct. Do you think you've got it down? Here's one final example. Pause the video and try to factor this one yourself. Let's see how well you did. First, we multiply the values of a and c to find the factors of that also add up to 11. Remember, two negatives also multiply to make a positive, so we have to consider these possibilities as well. But the correct combination in this case is 3 and 8. We can split the middle term into those two numbers, which allows us to group, then pull out GCFs of 3x and 4. With matching leftovers, all that's left to do is write the final factored form, 3x plus 4 times 2x plus 1. The grouping method can actually be used on any factorable quadratic expression, but it's easier to use one of the other shortcuts if possible. And remember, if none of these methods you've learned works, that just means the polynomial isn't factorable. In the next unit, we're going to factor quadratics a lot as we learn to graph, solve, and use quadratic functions in real-life scenarios. See you then!